Hi everyone, I'm Robert and I work for Kiwi.com, which is a European company, and we sell flight tickets. And that's all you need to know. I will be talking about Python memory management, and as the talk suggests, it's going to be like bits and bytes. It's not going to be like deep dive into like Python memory management works, because it's kind of broad topic and I'm by no means no expert in it. So I instead collected like some things which I found out about, and I find them interesting and I would like to share them with you. So, I think it's a good way to start a talk by by telling you what benefits it will bring to so why should you care about Python memory management? Like most of the time you don't have to, because for example I make up a number, in 95% of your work you don't have to care about memory management. So you don't need to know any kind of things here I present. So why do I care about Python memory management? Well, mostly because I find that topic interesting. I especially like any topic regarding languages, and possibility to know more things about Python, because the more you know about the underlying structure of Python, how Python work, you can write then better programs and be a better software engineer. And also, I like to think that after every year when I look back at my code base and when I look back at my knowledge at the year before, and I don't stand and think yeah, I was so stupid back in 1 year, right? And if I don't think so, I feel like I wasted my time becoming a better software engineer. So I think that's another good reason to get involved in Python underlyings. And also it may come handy for a job interview. People are asking things you usually don't need for your work to do. And also this is a merge request which was opened at our code base in my company, and somebody was trying to find memory leaks, and he was doing it very wrongly, which suggested that he knew nothing about how memory works in Python. So actually that's why I made this talk, to talk about how memory works in Python. So to start with this talk, it's okay. You can present with me if you want. So, the important statement about Python is that everything is an object, unless it's not. But most of the things in Python are objects. And every variable is just a reference to that object. Like when you have a variable, it's just pointing to some point of memory. And if you look at this is a structure which is defined in C language of Python, in C implementation, and every object contains this structure. And what this structure contains is, you can ignore this one, this is for debugging purposes, and this is the object reference counter, which is storing reference counting for the object itself, and this is the pointer to the object. This is the most important thing, I think, in objects, and every object, I think, should contain that. So, Python memory management overview. This is the overview how memory is being managed, and this is taken into account the physical memory, also kernel and virtual memory, which you don't have to care about. These are being operated by your operating system, and Python can't do anything with it. What's important here is the first layer. This is a heap in Python. This is like where all of the memory which is being used in Python is being stored in. And again, you can't do anything about this layer. The next layer, that's the layer we are going to talk about, because this layer is like is using the memory from the heap. And this is allocating like objects to memory. Like every time you create an object, this layer takes some memory from a heap, okay? And yeah. Also, yeah, this I don't know how to call it. It's taken from this file, and you can just look into it, and there's much more stuff written about it there. Okay, so how's memory allocated? This is taking into account like 64-bit CPUs. I don't really think that anyone still uses 32, right? So, like there is objects are being divided into two categories. One is objects which are bigger in size than 512 bytes, and those objects are being allocated by the malloc, which is like kind of straightforward and not really worth speaking about, I guess. And the other category are objects smaller than 512 bytes. And yeah, Python is using something which is called like simple segregated storage based on array of free lists. And there are like 3 levels of abstractions. The smallest level is block, then there is pool, and then there is arena. And as you remember, as I told you at the beginning, like everything in Python is object. And with that, like everything you create something, it creates object, and it's very, like allocating memory for every object would be really inefficient. And that's why Python comes with this simply segregated storage based on array on free lists. Maybe I could come up with some abbreviation for this. Okay. So let's start with block. Each block stores only one object. And block can be in size of from 8 to 512, which is the upper limit for the object creation. And there are 64 categories for blocks. And each block is a multiplication of 8. So you go from block size 8 to 16 and so on. Yep. Yeah, you can see it. This is the size of the block. Like what kind of objects belongs to that block. Like if you have block size of 4 bytes, it doesn't matter, it goes to the block of size 8. And it's using the ID for the blocks, so it's from 0 to 63, sorry. So then comes the pool. Pool is basically a collection of blocks, and every pool is storing blocks of the same size, and they are double linked lists if you care, but you don't have to. Okay, every pool has a size of 4 kilobytes, and each pool can be either full, empty, or used. And used pool is when it's neither full or empty, so there is still some place where you can store blocks, but it already has some allocated blocks in it. And then there comes an arena. Arena is a chunk of memory. This is like, as I told you at the beginning, like the second layer is allocating memory from the heap, and this is being like this memory is being taken for arenas. So every time when there is taken memory from the heap is either for arena or for some object which is bigger than 512 bytes. So each arena can have like 64 pools, because one pool has 4 kilobytes. And what's very important here is that arena returns memory back to system only if it's empty. So there can't be any pool or any block used in the arena. And that's very important because one of the things I was told when I was starting with Python was that Python is not returning memory back to the operating system, which is not true. Like in 90% of the time, it's true because it doesn't happen very often that arena is being like empty. So it doesn't happen very often that the memory is being returned, right? But memory is being returned for the objects which are bigger than 50 and 512 bytes, and also for empty arenas, even though it doesn't happen very often. If you want to, you can use this environment variable or this function, and if you start Python with this environment variable, it will print the usage of arenas and blocks and pools in your Python interpreter. I would like to show it to you, but I can't because I'm using Chromecast. But you can try it, it's very easy. You just define Python malloc stats equals 1, for example, you run Python, and it will output like all of the info regarding pools, arenas, and whatnot. And that info will be reprinted every time when you allocate new arena. So, with knowing this, this is very favorite thing running on Twitter and Hacker News regularly, like the small integers, like the trick when you compare identity of two integers and it returns true, and when you have some bigger integers, it returns false. So what it is that some integers are being pre-allocated, like at the beginning, like when the interpreter is executed, it allocates all of those integers, like -5 included to 25.7 excluded. These integers are being created at the start of the Python interpreter. Why? You may ask. Well, it's because it is like that. It's probably, the reason for it probably is like there is some statistics that those integers are most used integers, or maybe they are most used in the Python code base or something like that. So these are created at the start and are not being recreated later. Also, here is a link like when you can find, where you can find it in the C Python code. So next interesting thing, which I don't really think I ever saw it on Twitter, or people, and maybe everyone knows about it, and I didn't, is strings interning. And this is something similar to small integers. The basic concept is that some integers are not being recreated. That once you create, for example, foo integer, and the second time you try to create this, the foo integer, it's not being recreated. It's already being reused, the first one. Like, so when you try the identity of those two objects, it's true. But there are some rules like how it works. So if I remember it correctly, or I have it written somewhere. Yes. Oh, it's written there. So only ASCII cars are being pre-allocated, not pre-allocated, but interned, or how to tell it, I don't know. And ASCII cars must consist from letters, digits, and underscores. So if you, for example, use the exclamation point, it's no more true that the objects are identical. Also, you can use the interning with sys.intern. So you can enforce it also for any string you want. That's important to know. And what else is important? Yeah, the interning, the default interning happens at the compile time. So, for example, as here you define the foo is defined at the compile time, but this string foo is defined at the runtime. So this object is created at the runtime, and therefore, when you compare the second with joint, is no more identical because this string was created at the runtime. And also, what it means is that when you have string concatenating, like foo plus bar, is also identical to foo bar because foo plus bar is optimized at the compile time. Also, the article about this is here, and it's really good read, so you should go and read it. So, get size of. As I said at the beginning, I show you the screenshot of the merge request, which was trying to track memory leaks. What the guy did was that he was trying to use get size of to get size of the objects. But the problem with get size of is that it returns only the size of the structure of the object. So, for example, if you have list of integers and list of strings, which is in the same size, you would expect that like strings and integers takes different amount of memory, right? But when you call get size of on both of those lists, you receive like the same memory consumption, and that's because the list, its structure stores only pointers to those objects. So pointer to this object is in the same size of a pointer to this object. So it just returns the size of the structure, which is very important to know. So now we know about how memory is being consumed, like for objects. So it's a great time to tell you about how it's being managed. Do you know this guy? Okay, at least someone cool. It's Tony Soprano, and it's from TV series Sopranos, and he's running a business with garbage collecting. So, there are two principles in Python, like how memory is being managed. By manage, I mean collected. And first is reference counting. Reference counting is a very naive and simple idea. And as I show you, the basic object in Python with the object reference counter, this is where it takes its part. Like every time you use object or pass it somewhere, the object reference counter increases. And what reference counting does is that once the object reference count reaches 0, the object is destroyed. So it's very easy. It's very important to know that it cannot be disabled. And what else? Yeah, it's very simple, but it cannot detect cycles. Yeah. Here you can see how it works. Like you can get the reference count of the object. And do you know why? Like this is a clean start of the interpreter. And here I'm getting like the reference count for object A, which is 2. And do you know why it has already 130 references? Anybody? This is a clean start of the interpreter. So it's because of the small integers. Because the object 2 is being reused everywhere. It's not being created again. So we are just passing references. And every time we pass the reference, the object reference count is getting increased. So when we try to get the reference count of object A, in my case, on Python 2 running on Mac, it might be different. It's 130 already. And this is a newly created object. But when I pass it here, it already returns 2 reference count. Do you know why? It's what? Yeah, because we pass it to the function, and as we pass it again, the reference count gets increased. So that's why it's 2. So we know about reference counting, and the next thing is the generational cycle garbage collector. And what this does is that it tries to find cycles. And okay, I will tell you firstly how it works. So it uses like 3 generations of these are like categories. Like the first time the garbage collector is run, it stores all of the objects in the first generation. And everything that survives the first generation of a run is then moved to the second and then to third. The first generation is being run the most time. Like there is this threshold at which the garbage collector is being run. And once the threshold is reached, the garbage collector is running, and the lowest threshold is set for the first generation. So yeah, the lower generations are collected more often. And also, when the garbage collector is being run, all your code freezes. So it's better to avoid cycles, obviously. Yeah, here's like the example with cycles. You can see that I create a list, then append to that list to the list. I get the address of the list, which is the address in the memory. And I'm using the C types for getting the reference count. You can use C types to inspect like the C structure of objects. So it's 2, the reference count. But when I delete the list, you would expect like that the list will not be here anymore because you deleted it, right? But when you call the reference count, you will see that the list is still being somewhere referenced. And that's because of the cyclic reference, because reference counting cannot know that there is a cyclic reference. But when you call the gc collect, it finds the cycle, it knows that the objects are no more being referenced to it, and it decreases the reference count and destroys the object. And we are saved. So, what's the difference between del and del magic function? Well, as you saw in the previous slide, when you call del, like the built-in del, it doesn't destroy or delete the object. It only decreases the reference count. That's very important. Where the del magic function, it's called when the object is being destroyed. And it's important to know that in 99.99999% of time, you don't need to specify the magic del method, and don't do it, because once you do it, you will break the cycle finder for garbage collector, and those objects which has defined magic del method in a Python code will not be garbage collected, because garbage collector doesn't know like in what order to run in what order to destroy the object. So don't use it unless you have to and you know what you're doing. As a garbage collector, take a big price on the running time. The good thing to do is to break cycles, and you can break cycles in an easy way, like the break referencing, or you can use the weak references. What weak reference does is it creates a weak reference. And how it works. Basically, you can see it here. Like this is without the weak reference. B is referencing A, and when you delete A, decrease the reference counting, the B is still pointing to the object A. Because it still exists, it's still being referenced. But when you instead use the weak reference and once you delete the A, then you see that the B will return none, because it was only a weak reference, and weak reference is not being counted to the object reference count. And what weak reference does, it knows that the object doesn't exist anymore, so you get none instead, because it's dead. Also, a good thing to use is object graph, which can print like diagrams like this. It's very nice and probably useful. Or what you can do is disable the GC. And maybe you read the article from Instagram. It's really good article. Like the basic idea, what you do is that you run GC disable, and you should disable the garbage collector. But the problem is that some modules are enabling the GC in their code base. They are running somewhere the GC enable. So you can instead use the GC set threshold to 0. And then when you rewrite the threshold, the GC will never run again. So I will tell you more about the Instagram, because it's very interesting and it resulted in this merge request. So what I did, I guess most of you guys are running Flask, Django, whatever, using the VCGI or GUnicorn, right? And so what GUnicorn, for example, does, it creates the master process, and then it creates the worker from the master process by forking it. And the idea of forking is that when you fork a process, it is sharing the memory with the master process. And it's working on a method called copy on write, and that means that every time you modify the original object, is being like copied into your own process memory. Because if you don't modify the object, there's no like reason to copy this object to your memory, and instead the object can just share this memory in between them. This is very important for immutable objects, because they don't change their structure, and also there are some code objects in Python which never changes. But what Instagram found out is that instead of copy on write in Python, what happens is copy on read. Because every time the GC runs, it accesses the objects and it stores them in a list, and it alters the reference count for those objects. So those objects are being constantly, their structure is being constantly like rewritten, so it's taken as modified, and therefore the memory is being copied to the memory of your process, forked process. So what I did was that at first they disabled the GC, and they saved like a lot of memory because of that, which is kind of ironical, because they disabled the garbage collector, and also they saved some computing time. But then later, when the count of requests increased, they found out that the memory consumption is like raising linearly, and by that time, the pros of disabling the GC surpassed the cost of the memory for all those requests and all the objects which are not being garbage collected. So what they did instead is that they introduced the GC freeze. And what it does is, as you remember, I told you there are 3 generations in garbage collector. They introduce a new generation. And when you call GC freeze, all of the objects which exist at that time are being stored in the 4th generation. And for the 4th generation, the garbage collector is never run. So this is I think the best thing from this talk, especially if you are using the post fork more in GUnicorn or UVCGI. So what you will do in Python 3.7, it's not like released yet, is that pre-fork, you can call in pre-fork gc freeze, and it will freeze all of your objects. And so you will, save memory and computing time and whatnot. I got locked out from my computer. And new Macs are really cool. And my keyboard is broken. Because, like, the letters are sometimes stuck. Yeah, finally it worked. It gets stuck and I can't type my password because it's using the letters which are being stuck and blah, blah, blah. Stupid MacBooks. At least they are so cheap, right? So there are some tools you can use to track the memory. The first one is pytracemalloc. This should be in a Python 3.5, I guess, or 3.4, I don't remember. This basically tracks the memory usage per files. Yes, it's tracemalloc. In Python, yes, it's tracemalloc. Yeah. It's in 2.7.
Yeah, you should patch sources.
Yeah, but you have to patch sources. So, and the next thing is Pimpler, which is what I find cool about Pimpler is printing the difference count in objects created in between, different runs. What you do is you create the tracker. And once you print the diff, it will show you all the objects which are created. Then you run some function, and then you call print diff again, and you will see all new objects which are being created and allocated somewhere, which is really nice. So that's it. Thank you for being here. And also, if you have any feedback, feel free to drop an email. So thank you.